Now we are at a stage where I would like to discuss the supernode. What's the idea about the supernode? You see, when I wanted to say how much is the height of my body as a solid item, I have a metering tool and I would measure from my head to my toes. That's going to be a fixed value of some number, say 160 or 70, something. It's fixed. Now, another thing we did was that we had everything actually compared to the ground, and I was actually standing. I'm standing right now on the ground. My feet is on the ground. And therefore, when I want to talk about my head, the height of my head to the ground would be just the height of my body. So that's the relationship we get from the component voltage versus the node voltage. I want you to imagine that someone has made, in my shape, a balloon. The same size, the same structure I have, and he or she made a balloon out of my structure. The same size, the same height. So if that balloon is actually attached to the ground, suppose that this is that structure. I'm going to actually use this to explain what is happening. Well, something like this. Obviously, I'm a lot bigger than this one, but imagine that this is the balloon, right? If this balloon is actually connected to the ground, you can tell me what's the height of the head versus the ground. This is my ground. This metal part is my reference point, and it's ground. And this is attached to this by force to the ground. Because the structure as a component voltage has a specification, so much height, physical shape, pressure inside, you can actually tell me how much is the height on the top of the balloon would be. So that's what it is. But imagine the same balloon of my structure and my height and everything, someone actually pushes it into the air. Something like this. Something like this happens, right? When it happens inside the air and is floating, you will have difficulty. If you didn't know what my height is, you will have difficulty to actually measure it. Not only that, but you will have difficulty to tell me what is my end and what is the other end. Well, if someone has told you what's my height, that's something you can rely on. But what about this? How can you relate this versus this? This is floating. And as such, if this goes up, this may go up. If this one goes down, this will go down. The question is this: although the component voltage may be known to you, the component voltage itself may be known to you, you wouldn't be able to say anything about how much this is. You wouldn't be able to say how much this is. All you can say is this: how much is the subtraction of the two ends? This minus this, how much that is? Because that's the component voltage. That's the voltage of the component. That's fixed. No, it's 160 centimeters, for example, in the case of my height, right? So basically, the component voltage is known, but since you have no idea what is happening to this and what is happening to this, you can't say anything about them individually. All you can say in relation to each other, you can say something. You can say this minus this is this. That's all you can say. I want you to actually imagine the same structure we have on the screen right now. This is me, 10 volts. My feet are on the ground. Because my feet are on the ground, you can exactly tell me how much voltage on my head would be. This is my head. That's my feet. That's my head. This is me. Solid structure. I know 0, 10 volts on top, I get this 10. This is fixed scenario. But if someone says, this is not your reference node, this is your reference node. Let's go back. Someone says this is your reference node. You haven't solved the system yet. All you know is this. The plus side minus the minus side is 10. That's all you know. How much is the plus side? Can you say? No. How much is the minus side? Can you say how much that is in respect to the reference node? No. You won't know these until you write the equation and solve the system. The question is, if it is floating in space, how would you write the equation for it? If I know how to write the equation, I will solve this. If I know how to solve that, then I'm going to say exactly what is going to happen to the two sides of the balloon. So that's what happens when we go in and we introduce the concept of the supernode. If you go back to previous lectures, we said that KCL law is true in a single node, a very, very tiny node, right? In a very tiny scenario, we said that all the currents that come in have to be the same as all the currents that are leaving. It was a very tiny node in my mind. All the currents in, all the currents out, they have to be the same. Otherwise, the node is going to be unstable. It's going to explode. The same mentality is true if you actually consider any part of the design inside a balloon. Well, take a look at the Pearson Airport. If you go into, this is my Pearson Airport, right? And this is my structure. I have 3 people coming in, perhaps 4 people coming in. I have 1 people leaving, and of course 3 people would be leaving on this node. When I take a look at this node, a single node, 4 coming in, 3 leaving, 1 leaving. That's simple to understand. But I want you to zoom out your camera and actually see the entire airport as one big node in your mind. The entrance of this airport, you need to have eventually 4 people to get in order to go in. Then you have an airplane, you need to have this guy, this gentleman or the lady to actually leave through this airplane. You have another airplane and these 3 have to leave. If you actually put your entire structure inside a bubble, the entire airport inside a bubble, the number of people who enter this entire structure and the number of people who leave this entire structure should be the same. The structure is supposed to be empty when it comes to the midnight, for example. Everybody had to leave, including even the staff. So basically, whether I'm looking at a local point inside the airport, or I'm looking at the big structure as the entire airport, or even as a Toronto city, the city of Toronto, the entire city, eventually the number of people who come in during the morning and the number of people who leave in the evening, they should be the same. Otherwise, people come in, people come in, people come in. Obviously, it's going to be an unstable situation. You can't handle this. So the idea of the supernode is this. Instead of focusing on a single node, let's inflate the structure. Let's inflate a balloon and put it around a structure. The way we are going to do that, we are going to actually do it only on voltage source. Many textbooks actually do it over a voltage source and a resistor. I'm not saying that's incorrect. You can actually have anything, any part of this structure inside the balloon if you want. But I have seen many actually make mistakes by ignoring the resistors that go inside the balloon. So I don't want you to actually do anything other than the voltage source. So take a look at this. This is a balloon. So far it's floating. I don't know this. If this goes up, this one goes up. If this one goes down, this one goes down. Depending on what happens, it's going to be stable because all I know is this minus this is going to be 10. It's floating at this time. So what I'm going to do, I'm going to have a balloon only on the voltage source. Only on the voltage source. That's the structure. That's my Pearson Airport, the entire airport that I want to take a look. The entire George Barry building that we are in right now. So that's what I'm going to do. How many components are attached to this structure? On the left-hand side, you see two components are attached here and there to this side. On the right-hand side, you see these two structures are attached to it. If we follow the concept of Pearson Airport, of George Barry building, you need to count everything that comes in and everything that leaves. You can't just focus. That's one of the common mistakes I see inside the exam. You can't just say this side is equal to 0. Who said that? Of course, if this side is equal to 0, what happens to this? You can't do that. So basically, you need to say everything that is entering the bubble is equal to everything that is leaving the bubble. For this supernode, I need to start writing my equation. So here it is. This is Vx, this is Vy, and this is Vz. I have 3 nodes. But I know Vy and Vx are tied together. I know 10 volt is equal to the plus side minus the minus side. The plus side is attached to Vy. The minus side is attached to Vx. So if I know what Vx is, for any reason, if I know that this is 15, do I know how much this is? 15 plus 10, that's going to be 25. If I know this is 12, do I know how much this is? 12 minus 10 is going to be 2. These two nodes are glued through that bubble. We know that. So basically, I'm going to actually utilize this equation. I'm going to say, if I know what Vx is, Vy is going to be, take it to the other end, 10 volt plus Vx. First, I'm going to go in and identify how the balloon is. I'm going to go in and I'm going to say Vy is has already a relationship with Vx. It's going to be Vx plus 10. You already reduced one unknown. Your system previously had 3 nodes in mind, Vx, Vy, Vz. Now you have only Vx to find and you have Vz to write. The second thing is to write the equations for the supernode and the single node, which is a small node, which is Vz. So I need to write this supernode. Anything entering George Barry building is equal to anything leaving George Barry building. That's my supernode. If this is the biggest voltage of the universe, obviously this is going to also follow to be the biggest voltage of the universe. So if I'm assuming that these are the biggest one into the design, how are my currents going to go? Where are the directions I'm going to go? I'm going to say for supernode, I'm going to say on one end, left hand, just take care of all the components. Don't forget about anything. On the left hand side, Vx minus Vz divided by 2. I said this is the biggest, which means this is also the biggest, but this is obviously not the biggest in my mind, and therefore Vx minus Vz divided by 2 is leaving this node. Plus Vx minus 0 divided by 4 is leaving this node. It is the wrong time to say this is equal to 0. You can't say this is equal to 0. You have to continue. You have to finish all the components attached to the supernode or the bubble. I have 2 ohm. This is the biggest. Obviously, this is the biggest, just 10 volts extra. So it's going to be this way. So it's going to be Vx plus 10 minus Vz divided by 2. Vx plus 10 is the biggest. Vz is obviously smaller. And the current in my imagination is leaving that way. Vx plus 10 minus 0 divided by 8. I'm putting them inside the bracket because often I make a mistake by forgetting that if there's anything, these brackets could have a minus sign just in case. You need to put them in the bracket to be on the safe side. This is the equation for the supernode. let's go and write the equation for Vz. Vz is not really as much difficult anymore because we already know what to do with Vz. So let's write node Z. On node Z, what do I see? Again, these are the things that come to your mind immediately. You have 3 components attached to the Vz. 5 amp is actually forcing itself to the design. Then I have Vz is the biggest one in the universe. Vz minus Vx is leaving, so it's going to be Vz minus Vx divided by 2. Vz minus Vx plus 10. You see this bracket? If you don't have this bracket, you might be in trouble. Divided by 2 is equal to 0. Although extracting the equations a bit more challenging, but eventually, if I solve this system, I'm going to get the same component voltages, the same component currents, the same component voltages and currents. The voltages of the nodes are going to change. Why? Because previously, this was your reference node. As soon as your reference node is changing, the voltages of the nodes are going to change. But the component voltages and component currents are exactly the same. Whether you assume this is to be 0, this is to be 0, this is to be 0, or this is to be 0, at the end of the day, the component voltages and currents are supposed to be exactly the same. So let's go. I want to actually solve 2 more Supernode and get you a bit of a feeling before I go into the mesh equation. Let's try one more. Okay, this is actually an example from the textbook, page 89. I have 4 ohm. I have 2 ohm. A voltage source. Six, 8, 10 volts. What the book did, which is not incorrect of course, but it is confusing to many of us, is to actually assign currents. When you go into the solution I posted for chapter 3, you find 2 solutions. One solution is based on what I'm trying to explain today, and one solution is based on the book technique. I have seen through many years of teaching this class that the book technique, although correct, is not really helping our students to learn this properly. What do you have in front of you? That's a few questions you have to answer in a flash of a light. You have 4 resistors, 2 voltage sources, right? You have nodes. Where are the nodes? This is 1 node, 2 node, 3 node, and this. How many loops do you have? Basic loops, 1, 2, 3. You can imagine if I wanted to go through chapter 2, I'm going to end up having so many equations, so many unknowns to solve. But I want to use the nodal equation to solve the system. Now, take a look at the power supplies. You have 2 different power supplies. If I just need to go and pick up my reference node. If I pick up this one as my reference node, I'm going to ground this guy. This one is going to be grounded on the negative leg. Therefore, I would know how much this is. But this one is kind of a dangling one. This one can go up and down like a balloon boy. This goes up, this one goes up, this one comes down, this one comes down. I have no idea. That's my supernode. If I choose as my reference node here, I have grounded this power supply on one end. Therefore, I would know what this voltage is. But this one, I have no idea. The only thing I know is that the value of this component is 10. But if this one goes up, this one goes up. If this one comes down, this one comes down. It's kind of floating in this space. So you have no choice. There is no trick to this. You have to deal with the Supernode technique in this case. So let's go and say I'm going to assign this as my reference node. This is my 0. This is my reference node. Let's name this. This is node A. This is node B. And this is node C. Let's begin first massaging the design a bit. This 10 volt is equal to the plus side minus the minus side. The plus side I can see is attached to VA. The minus side I can see is attached to the ground. And therefore, safely so, I can say that A is 10 volts. Please note, this 10 volt is not the same as this 10 volt. This 10 volt represents the component voltage. This 10 volt represents the node voltage. The node voltage could be anything, and still the component voltage could be 10. So that you have to be conscious about. Where is my supernode? My supernode is going to be this one. I'm going to only include the power supply. Okay? I need the space, so maybe, okay, let's see how it goes. Eventually I'm going to erase this part. This is my supernode. The component voltage is 5. The component is attached between B and C. 5 volts is equal to the plus side minus the minus side. Plus side is attached physically to node B. Minus side is attached to node C. Well, my mind says that if I know what node C is, all I have to do is to add the height of Cameron to get node B. So because that's the way it is. This is my feet, this is my head. If I added it, I'm going to get B. So what happens, VB is equal to, this goes to the other end, 5 plus VC. 5 plus VC. So I'm going to remove this and say this is VC plus 5. This is VC and this is 10. Of course I can write a KCL law for this, but in order to do that safely, you need to define a new variable that is the current of this power supply. This current has to be identified, otherwise you cannot write. I don't have to write it. Why? Because the purpose of writing nodal equation is actually to find the voltage of the nodes. And the voltage of the node I already know. So this is going to be the case. So let's see. How many nodes do I have? Again, these are not things that you would ask and you take a sip of water to answer. How many nodes do you have? This is node, you have a supernode, one equation, one unknown you expect. This supernode, how is it attached to my design? On the left hand side I see 2 and 8. On the right hand side and the top, bottom and top, I have 4 and 6. I have 2 on the right hand side, 2 on the left hand side. I need 4 terms in my supernode. Let's begin on the left hand side. This supernode is the biggest one of the entire design in my mind. Therefore, all the currents are actually leaving from the node except the one that is pushed into the node itself. Nothing is pushing itself or extracting itself from the node. So I'm going to say on the left-hand side, VC plus 5 minus VA, that is 10 divided by 2. That's this guy. VC plus 5 minus 0 divided by 8. That's the next one. I have seen inside the class and in the exams, many people simply say this is equal to 0. That's very wrong. This is the entire structure. These are the main entrance of Pearson Airport. This is the flight that is leaving to London, and this is possibly some other exits of the Pearson Airport. You have to count all entrances, all in and out of the building. So you need to go and continue the task. On the right-hand side, you are going to see VC on this side. VC minus 0 divided by 6. You can see while on the left-hand side I did VC plus 5, on the right-hand side I'm doing VC. That's a bubble. The two sides are different. So it's going to be plus Vc minus 10 divided by 4 as equal to 0. One equation, one unknown. It's going, as soon as you find Vc, you know what Vc plus 5 is. As soon as you have all the voltages, you have this current, this current, this current, this current, all the voltages are known. That's the purpose of Supernode. I want to go in and I want to solve two questions that I recently asked everyone to look into. So let's take a look. Let me try one of them actually. This is a bit of a funny one. Let's take a look. Okay, this is problem 332. We would like to find the voltages of the nodes. These are kilo, first of all. When you say this is kilo, 5 kilo, and remember in the nodal analysis, the resistivity goes under the fraction, so it's a denominator. So anything divided by the kilo is going to give you milli. That's why I'm going to be happy with this milliamp, because everything seems to be the same unit. Okay? Do I have a supernode? If this is a reference node, how much is this? This is 12 volts. One end is 0, the positive side is this. So 12 is equal to the plus minus the minus. Plus minus 0, this is going to be 12 volts. If this is 12 volts, how much is this? 20 is equal to plus minus the minus. 20 is equal to plus minus the minus. The plus side is 12. The minus side, I don't know. Let's find it. Minus side goes to the one end. It's going to be 12 minus 20. So this is going to be minus 8. 12 minus 20, that's minus 8. How about this? You have 12 volts, you have 10 volts, and this one. 10 volt is equal to the plus side minus the minus side. The plus side is 12. The minus side, I don't know. So you take the minus side to one end and the constant to the next end. 12 minus 10, that's 2 volts. This is not a supernode. This balloon is grounded. This balloon is also grounded through this balloon. This balloon is also grounded through this one. Everything is grounded in one end. This structure is firmly grounded by in this end. Therefore, you don't have a supernode. You actually don't have to worry about it. Everything you know. You know this voltage, you know this voltage, you know this voltage, you know the current, the voltage, everything you want to find. Let's go in and solve 3.28. The concept of the supernode, if not exercised good enough, is usually the biggest challenge in the midterm and the final. And that's why quiz number 2 is going to be considering supernode. I need everyone to consider the supernode. That's a challenge. Let's go for 3.28. Okay. I want to solve this design through two different approach with two different grounds or reference node. Everything is in ohm. Okay. Question is, solve the system. If you want to go with chapter 2, you have 1, 2, 3, 4, 5, 6, 7, 8, 16 unknown. You have currents of these two guys. 18. Of course, you can simplify these currents because they are the same on these branches. So 16, 18, these are the number of unknowns, which means your system is going to be 16 or 18 equations, 18 unknown. That would be a huge task to do, especially if you want to do it manually. Especially when you want to write it at any time, that equation can actually be wrong form of equation. Well, let's begin. The first thing you need to ask yourself is, where is my ground? Where is my reference node? Again, one more time, ground and reference are different slightly, but I'm going to use them freely in this topic, in this class. I'm going to assume this is ground. If I ground this, the head of this balloon is grounded. The feet of this balloon is grounded. These two are actually grounded. I want to see how much this voltage is. It's going to be 60 volt is equal to the plus side minus the minus side. The plus side is 0. The minus side, I want to find it. So obviously you can see it's upside down. It's upside down. This is going to be minus 60 volts. When I get to this one, 90 volts is equal to the plus side minus the minus side. The plus side, I don't know. It's not upside down. That's good news. So plus side minus the minus side is 0. So it's 90 is going to be plus the voltage, the plus side. So this is 90 volts. How many nodes are left? 1. Let's call it A. 2. Call it B. 3. Call it C. And this 4. Call it D. This is one big node. Okay? Thanks. We found the two nodes voltages, and therefore we don't have to write KCL law for this one. Nodal equations for these two. Of course, if we want to, we can, provided that we have defined currents and currents. That's a different topic. But you have 4 equations for unknown to write. Let's begin. So for node A is the biggest one. VA minus VB divided by 8. VA minus VD divided by 4. VA minus 90 divided by 8. This 8 is equal to 0. 3 components attached, 3 terms you have. Let's go for node B. VB minus VD divided by 5. Now B is the biggest one in my mind. VB minus VD divided by 5. VB minus VA divided by 8. This is the biggest one. VB minus 0 divided by 16. VB minus 0 divided by 16. VB minus VC divided by 20. VB minus VC divided by 20 as equal to 0. Remember, first of all, you have 4 components, you have 4 terms. The nature of this fraction is amp, 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 and amp. The nature of the terms have to be the same, otherwise you won't be able to add apple and orange. They have to be the same nature. Okay? So that's node B. Let's do node C. Node C, VC minus VB divided by 20. Now I'm assuming C is the biggest one. VC minus 60 now. I'm careful with the bracket. VC minus D divided by 10 as equal to 0. VC minus D divided by 10, VC minus VB divided by 20, VC minus 60 divided by 4. I took care of this, this, and this. I need to take care of the D. Let's take a look at the D. How many components are attached? 1, 2, 3. I need to find it. So it's going to be VD is the biggest now. VD minus VB divided by 5. VD minus VA divided by 4. VD minus VC divided by 10 as equal to 0. This is where the big chunk of the grade rests. You need to write this correctly. Simplifying is the next stage, solving the system is the next one, and getting the number is another one. So in this case, because it's a 4x4 system, and your calculator cannot handle 4x4, you need to manually eliminate one of the unknowns. Make it 3x3 and then use the system. Obviously, that's not the intention for us, to give you a 4x4, either in the midterm or the makeup. That's not the intention. But it does happen quite often 2x2 or 3x3. So 3x3 is acceptable, and the pressure and the workload for a 3x3 is the same as 2x2, because you just simply punch in the numbers into the calculator. So far, I solved this system assuming a regular structure and a regular understanding. But if you take a look at 3.28, you can see that the reference node is somewhere else. The reference node is in the middle. So let's go and follow what the book says and change the reference node and see how the equations are going to be written and applied. Okay. The book says this is your reference node. I'm going to erase this part. The question you need to ask yourself is, are my power supplies, the voltage sources, are they somehow grounded? I don't see any connection between this and the ground. I don't see any connection between this and this. So I do have a supernode. The next question you need to ask yourself is, where is my supernode? As we discussed, and this is something that comes with imagination, the balloon I'm going to exert is going to include only the voltage sources. So my balloon is going to be this. That's my balloon. Do I have a resistor inside? No. Do I have only power supply? Yes. How many nodes do I have? How many connections do I have? I have one connection on this, one connection on this, and one connection on this. If I assume this to be Vx, do I know anything about this and this? Yes, I would. This is Vx, this is Vx, this is Vx. So let's call this 90 volt is equal to the plus side minus the minus side. And plus side is this one. The minus side is basically Vx. Take Vx to the other end. V plus is equal to 90 plus Vx. This voltage is 90 plus Vx. I need to deal with this balloon before I go and write my equation. So it's very important to write them properly. If this is Vx, how much is this node? This is Vx, this is Vx, this is Vx. Plus side is Vx. 16 is equal to the plus side minus the minus side. Plus side is Vx, I'm sorry. Plus side is Vx. Plus side is going to be Vx. The minus side, I don't know, I want to find it. So minus side comes this side, 60 goes the other end. Minus side becomes Vx minus 16. So this is going to be Vx minus 16. So after this, what do I have? I have a ground, I have a balloon, supernode. I have Vy, I have Vz, and I have V theta. Still I seem to have 4 equations for unknown. Obviously, in such a scenario, through exercise, you would know which one is easier to write, but nevertheless, the challenge is there. So let's take a look. Okay, let's remove this. I need the space. I want to write the equation for this, this, and this before I write the big one, because when I finish these 3 nodes, I need to erase the space so that I can actually put the supernode equation on the table. Let's go for V theta. V theta interacts with Vz through 4, with 0 through 5, with Vy through 10. V theta minus Vy divided by 10. V theta minus 0 divided by 5. V theta minus Vz divided by 4 as equal to 0. 3 components, 3 terms. 1, 2, 3. 1, 2, 3. Nature current, current, current as equal to 0. That's theta. When I get to Z, I'm assuming Z is the biggest one and everything is actually leaving the node. So it's going to be Vz minus V theta divided by 4. Vz, this is going to cover this guy. Vz minus 0 divided by 8. Vz minus 0 divided by 8. Vz minus this node. Vz minus this node divided by 8. So Vz minus, open bracket, 90 plus Vx divided by 8 as equal to 0. Let's look at Vy. Vy is interacting with 0 through 20. Vy interacting with V theta through 10. Vy is interacting through this with this node through 4. So I need 3 terms. I have 3 components. I need 3 terms. So it's going to be Vy minus 0 divided by 20. Vy minus V theta divided by 10. Vy minus Vx minus 60. Remember this bracket, please. Divided by 4 as equal to 0. This bracket is going to save you a lot of headache because, especially in the exam, when you don't find the solutions match, you're going to be a bit confused. Although it's helping many to clear the scenario, it's actually confusing for some. You need to make sure you follow the instructions properly. Vy minus that voltage, and that voltage is entirely inside a bracket, because this minus and minus is going to give you a plus. That's why. You need to be careful on that. What did I do? I wrote the equation for this, I wrote the equation for this, and I wrote the equation for this. I need to write the equation for the supernode. Let's do that. And then I'm going to actually attack one more circuit before I go for the mesh. I need 4 equations for unknown. I wrote this, 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 and I need to write the supernode. And I need to erase this space because the supernode takes a bit of a space itself. That's the 4th equation for us. Okay. The supernode has 3 nodes attached to it. This one, this one, this one. The supernode interacts with Vz through 8 ohm on this side and this voltage. Through 0, with 0 through 16 ohm on this side. With Vy through 4 ohm on this side. And each side has its own voltage. And I need to be careful on that. So let's begin on this. 90 plus Vx minus Vz divided by 8. Vx minus 0 divided by 16. That's the second one. And then Vx minus 60, that's the node voltage anyway, minus Vy divided by 4 is equal to 0. Please remember, I just continued this. It's a big equation which covers the 3 components attached to it. Let's try one more example. And this example is 3.34. Okay. The circuit in 3.34 looks as if this is a 3D circuit. So I have 1 ohm, a power supply, 2 ohm, 3 ohm, 4 ohm, 6, 7, 5. This just says that I'm bypassing this wire. If I'm connecting anywhere, that's going to be a node. Okay? But if I'm showing this, it means I don't intend to intersect this line. I'm going to bypass the line and continue. I'm going to solve this design through 2 different techniques. One, I'm going to have a very nice and clean reference node that helps me to write my equations. Then I'm going to actually change and modify my reference node, make this a topic of a supernode. Well, you happen to have 1 voltage source. That's really good news, because all you have to do is to go into the negative pin and actually pick up your reference node. As simple as that. This is 0, this is 0, this node is 0. Please remember, this is all 0. I want to put these zeros in so that everybody knows what's happening. What are the nodes? This is 10 volts. One end you have minus, the other end you have plus. 10 is equal to the plus side minus the minus side. Plus side, I don't know. Minus side is 0. Therefore, V plus is 10. This is 10. This is Vx. This is Vx. This is Vx. I need to be careful. This is all Vx. This is Vx. It's 1 node. This is Vy. I don't have to go and show it everywhere because all the components are nearby. This is Vz. This is Vx. Sorry, this is Vx. And this is Vx. This is Vy. Vz, and as you can see the line, this is Vz. Okay? So I want you to be careful about this. I want to clean it up a bit because usually that is not what it's meant to be. When I say Vx, I know this is all Vx. So that's one thing I need you to remember. That's one node. This is VZ, and everything is VZ, so I'm going to clean this up. This is all 0. I'm going to clean it up. Now we are in good shape. This node, you already know what the voltage is. You don't have to write the KCL law for it. Let's write the KCL law or nodal equation for Vx. Vx minus 10 divided by 1, Vx minus Vz divided by 2, Vx minus Vy divided by 6. That's all. You have 3 components attached. Vx minus 10 divided by 1, Vx minus Vz divided by 2, Vx minus Vy divided by 6 as equal to 0. Let's take a look at Vz. This is Z. 2 ohm is attached, 7 ohm is attached, 5 ohm is attached, 3 ohm is attached. You have 4 terms, you write 4 equations, 4 terms, 4 components, 4 terms. So it's going to be Vz minus 10 divided by 7, Vz minus Vx divided by 2, Vz minus 0 divided by 5, I'm taking care of this, and then Vz minus Vy divided by 3 as equal to 0. Let me write it down on this end. I wrote Vx, I wrote Vz, I need to write Vy. Vy 3 ohm, 6 ohm, 4 ohm. Vy Vz 3, Vy Vx 6, Vy 0 4. Vy Vz 3, Vy 0 4, and Vy Vx 6 as equal to 0. That's one equation, that's another equation, and that's the next one. 3 equations, 3 unknown. Solvable. In this scenario, the reference has been in a proper place, and it has given us a chance to simplify the equations in one sense. I want to go in and attack the system again, but this time I'm going to put the reference node in a difficult position. Let's go back in. As soon as your reference point changes, you cannot rely on the voltages you found through the previous arrangements. Suppose this is my ground. Do I have a supernode? Yes, this one. Any power supply is going to go into my balloon. This is my balloon. If this is VA, obviously now it's very easy for us to say how much this is. 10 volts on top of VA, this is going to be 10 plus VA. That's the voltage of this node. This is VB, this is VC. That's it. I need to write C and D as the regular ones, but then I need to write this as my supernode. I shade the labels or index of these voltages because as soon as the reference node is changing, the equations are going to change, the solutions of the voltages are going to change, but remember at the end of the day, the component voltage and the component current would remain the same. Let's write VC. What do I see? VC 2, 0. VC 6, VB. VC, this voltage, 1. Let's begin. VC minus 10 plus VA divided by 1. VC minus 0 divided by 2. VC minus 6 divided by, minus VB divided by 6 as equal to 0. 3 components, 3 terms. Current, current, current. Let's go for VB. VB 0, 3. VB VC 6. VB VA 4. VB 0, 3. it's really worth it to be patient and to write the equations properly before you jump in to simplify and solve it. Because if you make a slightest mistake on writing the equation, it's going to show up all the way to the end. Write this carefully as much as you can, and then move on to the solution. VB minus VC divided by 6. VB minus VA divided by 4 as equal to 0. That wasn't bad. This one and this one. Now I have a balloon. This balloon, I have to see it correctly. I have two components, 5 ohm and 4 ohm attached on this side, and I have 7 and 1 attached to this side. I need to write 4 terms. I can't stop halfway through. I need to say these plus these are supposed to be equal to 0. So let's begin on this side. VA, VB 4, VA 0, 5. I want to choose different colors. VA minus VB 4, VA minus 0, 5. That's this segment. But you need to continue. You need to continue for these two. 10 plus VA and 0 and 7. 10 plus VA and VC and 1. 10 plus VA and 0 and 7 plus, please continue. This is the way we are going to continue. 10 plus VA minus VC divided by 1 as equal to 0. We have had the chance to go through many cases you can see from the design, from the end of the book. Sometimes you can actually attack them as a regular nodal equation to solve, and sometimes you can manipulate the design, put the ground somewhere else. Typically speaking, inside the quiz or inside the midterm, most of the time we pick up a design from the assigned questions, from examples of the textbook, from practice questions of the textbook which are inside the chapters, from the end book questions. We modify numbers, perhaps a bit of a structure. Most likely we place the ground somewhere else. So you are not going to see exactly the same identical circuit inside, but you are going to see comfortable similarities between what you are going to see in the quiz and the midterm versus what you are going to see inside the textbook. So in one sense, you have seen it. All you have to do is to practice. The misconception in this class is this: I understand the topic, I can do it when the exam comes. That's the biggest mistake you can do in this class, because all I can do is 10% to help you. You need to actually pick up the pen and pencil and do the 90% of the job, and that's on your shoulder. We are here to help. Let's see what we can do. Thank you very much.